So in this somewhat shorter pencast, I just want to talk about what we might call spanning observations. So this is the kind of thing that will turn out to be very useful in various situations, and which is now pretty easy actually to prove based on our work on the continuous functional calculus. So let me just put some notation here which is standard, and we haven't actually used it yet. I will also discuss it at the lectures. So what this is often called ASA is just a set of x's in A. A is a C-star algebra, of course, such that x is x star. So it's just a subset of all elements in A that happen to be self-adjoint. And then A plus will be the x's in A, having the property that there exists y also in A such that x is y star y. So this is just the positive elements, and it's worth noting that this is the same as the intersection of the set of the self-adjoints and the x's in A that happen to have the spectrum contained in R plus. Right? So this is a big result about positivity, is that you can either define it as having such a y, or you can define it as being normal, or you can define it as being self-adjoint and having the spectrum contained in the positive real axis. And then finally, UA is standard notation for the x's in A that are unitaries. So x star x is 1 is x x star. Right? So we've had various colors for these. I'm not sure I remember, but this is self-adjoint, and so positives and unitaries. Okay, and the observations I want to make is that first observation, A is the span of ASA, and also ASA is the real span of A plus and the real span of UA. So you see the issue that I've tried to put into the notation is that, of course, the self-adjoints as a subset of A is not a subspace, because A is a C-star algebra, and the C-star algebra is, as a vector space, it's over C. Right? So if we were having a subspace of A, it would have to be closed under multiplication by complex numbers. Right? But the self-adjoints do not have that property, because if I take a self-adjoint element and I multiply it by I, it will stop being self-adjoint, because when I take its star, we will get a minus I out instead. Right? So the self-adjoints is a real subspace. Right? So if you were considering your complex C-star algebra as only being acted on by real numbers, then it would be, as a vector space over the reals, it would be a subspace. And then so that's the second bullet that says that if we think of if we sort of forget about the complex numbers and just think of real numbers, then we can write any self-adjoint element as a linear combination of positive elements and also of unitaries. And this is sort of said in a way that is very general, but also perhaps gives a bit of a wrong impression of how many elements you need in a linear combination, because actually you only need 2 in all of these cases. So you can get by with very small linear combinations. Right. So the first one, I'll call this, this is the complex one, and this is the real one, if you like. Right, and the complex one, we've actually done this before, but I just wanted to point this out, right? So I can write x as the real part of x plus I times the imaginary part of x, and then the point is, of course, that this lies in ASA, and this lies in ASA. That's the whole point. And I made a linear combination where the coefficient to the left is 1 and the coefficient to the right is I, and that's fine. It's a complex number. That's what I need. And of course, I need a complex number to get out of the self-adjoints, right? To reach x in case x is not self-adjoint. Right. So this is easy to see, and actually the first one of the real versions we've also done already, because I've seen that if x is self-adjoint, and then the point here is that I can write x as x plus minus x minus, and the way I do this, let me just remind you, the way I do this is I look at these two functions, one that we could call f plus, defined this way, and another function, another function we could call f minus, defined like this. And then we just take the functional calculus and define x plus to be f plus of x in the functional calculus and x minus to be x minus of x in the functional calculus. By the sort of spectral mapping property of the functional calculus, the spectrum of x plus will be contained in the positive axis because it's the range of f plus, and for the same reason x minus will be positive. And it's easy to see that when you subtract these two functions, f and f minus, you get this function here. You can draw in green. Maybe I'll use like this. Right, so this function here, and that's just the identity function. So the difference of the elements will be precisely the element corresponding to the identity, and that's precisely x. Right? So this is something that we have done already and used already. So I also have a version with unitaries, which I think is a little bit more interesting. So we may assume that the norm of x is less than or equal to 1, right? Because I want to convince you that I can write x as a linear combination of unitaries, and if the norm of x is bigger than 1, then I will just multiply on some scalar, making the norm less than 1. Then I do the linear combination there, and then I can multiply on with scalar reciprocal, and then that will give me what I need. And now, so then I will consider a very concrete map. Let's call it f, from -1 to 1 to c, defined by f of t is t plus I times the square root of 1 minus t squared. So you can see it's important for me that my t is in absolute value less than or equal to 1, because otherwise I would have to take the square root of a negative number, and even though I don't mind complex numbers in this setting, then would at least would have to come up with some sort of definition of that. So this is completely real, except of course for the explicit non-real thing, namely the complex number I, which is given there. Right, so it's a complex valued function, as you can see, but only in the limited way of having such a constant I. Then let's note that the absolute value of f of t, or the modulus, let's say squared, that's just the square of the real part plus the square of the imaginary part. And then this, of course, just becomes t squared plus, so 1 minus t squared is a positive number because t is now a negative number because t is between minus 1 and 1. So so when I take the square root and square, I come back again. Right? So that's just 1 minus t squared, and this becomes 1. And also, I can note that f of t's complex conjugate is t minus I, 1 minus t squared. So what does that give me? So that gives me, I'll do one more observation, namely that the real part of f of t is, of course, just t. Right. So these are sort of basic observations about my function f. It's a little bit hard to draw the graph of f because it's complex valued. But you can sort of see that if I was to draw the graph, I could sort of think of it as a curve, right, in the complex plane, right? So maybe you can draw it this way, right? So here's the complex plane, and I would like to draw for you the unit circle, right? And then the point is that whatever this function does, it starts at minus 1, where the value is I think minus 1, and then it sort of runs around in some way. It's not so important how it does it, but the essential observation here is that, of course, since the absolute value of f of t is 1, then all the action takes place within the unit circle, and this is essential here. So I will let u be the same as f of x, where I'm using functional calculus on x, noting that the spectrum of x lies inside the interval where I define my f, right? Because x is a self-adjoint element, so that means that the spectrum is real, and its norm is less than 1, so that means that the spectrum has to be between minus 1 and 1. So since f of t is in T for all T, which is just the sets of modulus 1, for all T in that interval, or maybe actually it would be more appropriate to say for all T in the spectrum of X, we get that the spectrum of f of x is contained in T. So f of t is a unitary, right? Because it's normal, and the spectrum is contained in the unit circle. Maybe I should write this out, right? Because f of t is what I'm calling, it's what I'm calling u. So I'll write like this. And of course, x is going to be the same as the real part of, maybe that's the wrong way of saying it, x is going to be the same as, maybe I'm sort of painting myself into a corner a little bit, so and because t is the same as the real part of f of t, which is the same as the average of f of t with f of t's complex conjugate, then we get that x is the same as the average of u and u star. Right? That's the continuous functional calculus again, right? Because t is exactly the function which we usually call the identity function. Right? So it corresponds in the functional calculus to the operator x. And f of t is exactly the function that corresponds to u, and the complex conjugate of f of t, is what corresponds to u star. Right, so I've created, I've been able to write x as a linear combination of two unitaries, namely u and u star. And this is what I wanted to know, so it will lie in the real span of the unitaries of A, which is what I wanted to prove.